In our last lecture video, we introduced some key aspects of IR spectroscopy, including the intensity of signals, the types of vibrations, and common vibrational frequencies. In this video, we'll look in more detail at some of the common frequencies that you'll encounter, and then we'll apply these concepts to the analysis of some IR spectra. We'll start with CH bonds because every organic molecule you'll encounter will have CH bonds. Here, as we saw before, the hybridization of the carbon influences the vibrational frequency. And the carbons with more S character will have higher frequency vibrations. That means that alkyne CH bonds will have a higher frequency than alkene CH bonds, which will have a higher frequency than alkane CH bonds. The next functional group we'll look at is carbonyls. One of the most characteristic stretches that you'll see in an IR spectrum is the carbon-oxygen double bond stretch of a carbonyl compound. And within the class of carbonyl compounds, there are two factors that can affect the stretching frequency: resonance effects and inductive effects. And we looked at both in more detail in the last video. So now, considering those two factors, let's try to order the carbonyl compounds shown here in terms of carbon-oxygen stretching frequency. In order to do this, we first need to remember our functional groups and draw out the structures. Then we should think about which carbonyls have resonance effects that might decrease the carbon-oxygen stretching frequency, and which carbonyls have inductive effects that might increase the frequency. The amide and the acid both have resonance structures that can be drawn with the lone pair of the oxygen or the nitrogen atom, and that will result in a lower frequency CO vibration. Carbonyls like acid chlorides will have inductive effects that increase the stretching frequency of the carbonyl. And ultimately, we can order the carbonyls as shown here, with the acids and amides on the right or at lower frequencies, and the anhydride or acid chloride on the left at higher frequencies. And the values on top are the approximate frequency that you can typically expect to see a particular kind of carbonyl stretch. For example, if you see a strong stretch at 1715 wave numbers, then you'd expect that to be a CO double bond stretch. But you can also be more specific, and now you can say that it's most likely a ketone CO double bond stretch. A CO double bond stretch at 1735 wave numbers is most likely an ester, and so on. If you wanted to be more confident in your assignment, then you could look for additional stretching bands. For example, if you were deciding between a carboxylic acid and a ketone, then you might also look for the OH stretch of the acid. The additional vibrational frequencies that you might use to help you distinguish between different types of carbonyl-containing compounds are included on the bottom of this slide, and we'll see them in more detail as we move forward. Now let's try an example. What type of carbonyl compound gives rise to the IR spectrum shown here? In order to answer this question, we need to first identify the CO double bond stretch. So we look between 1650 and 1800, and we see this band here. This band is right around 1800 wave numbers, which is on the high end of a carbonyl stretching range, and more specifically, it's in the range for an acid chloride. We don't want to stop there though. We want to look for another peak that can help corroborate that assignment. So we would look for the carbon-chlorine stretch between 550 and 730 wave numbers. And we do in fact have a band in that range. So an acid chloride is a good assignment for this spectrum. While carbonyls have one distinctive stretching frequency, other functional groups will often have more than one. Alcohols and phenols, for example, have both an OH stretch as well as a CO stretch. And we can use both of these stretches to help us assign an alcohol. The OH stretch occurs at very high frequencies, far to the left of the spectrum, between 3300 and 3600 wave numbers. These stretches are usually very intense and also very broad. The other important stretch for alcohols is the CO stretch. This stretch appears between 1050 and 1220 wave numbers, and it can help us determine what kind of alcohol we have. If we have a primary, secondary, or tertiary alcohol, or a phenol. The OH stretch could do that too, as shown in the column to the right, but the OH stretch is usually so broad that in practice that's not very helpful. Amines are similar to alcohols and will feature an NH stretch as well as a CN stretch. In this case, though, the NH stretch is often the most helpful feature. Like the OH stretch, the NH stretch will also appear between 3300 and 3500 wave numbers. These stretches are not as broad as OH stretching bands, and the number of NH stretches that we see will tell us what kind of amine we have. If we see only one NH stretching band, then we probably have a secondary amine. But if we see two NH stretching bands, then it's most likely a primary amine. Let's look at two examples. Determine if each of the spectra below result from a primary, secondary, or tertiary alcohol or amine. We want to start our analysis by looking for the OH or NH stretch. So we'll look between 3300 and 3600 wave numbers. In the top example, there's an intense and broad peak, and this is very characteristic of an OH stretch. This is likely an alcohol. So then we should look for the CO stretch. These appear between 1050 and 1200 wave numbers, and in this spectrum we have a peak right about 1100 wave numbers, so this is most likely a secondary alcohol. In the lower spectrum, in our OH and NH stretching region, we have two short, not very intense peaks. These are NH stretching peaks. These are sharper and less broad than the OH stretching bands. Now to determine what kind of amine we have, we just count the NH stretching peaks. Here we have two, so we have a primary amine. The carbonyl CO double bond stretch and the OH and NH stretches are the most characteristic and often most helpful stretches in the IR spectrum, so we spent most of our time on those. But we'll also look more briefly at other functional groups and what to expect from the IR spectra of these structures. Ethers have one diagnostic stretch, and it's the CO single bond stretch. We just saw this stretch when we discussed alcohols, so to identify an ether by IR, you're looking for the presence of the CO single bond stretch, but the absence of an OH stretch of an alcohol, or the absence of the CO double bond stretch of an ester. Very symmetric ethers will give rise to two distinct bands, and this is because there's a symmetric stretching mode and an asymmetric stretching mode. For ethers that are highly symmetric, meaning the two organic groups of the ether, the two groups bound to the oxygen, are the same, then there's only one CO stretching mode, because now only one mode changes the dipole moment of the molecule. Alkenes will have two characteristic bands. The CH stretch of the vinyl, or the sp2 CH bond, will appear just above 3000 wave numbers. Remember that the alkene CH bond is at a higher frequency than the alkane CH bond, and so it is more distinct in the spectrum. Alkenes will also have a carbon-carbon double bond stretch, but this stretch will only be visible for alkenes that are very asymmetric, where one side of the alkene is very different from the other side. That means that internal alkenes, like the one shown here, will have weaker carbon-carbon double bond stretches than terminal alkenes, like the one we saw on the last slide. Alkynes will also have a CH stretch at a higher frequency, around 3300 wave numbers. And alkynes will have a carbon-carbon triple bond stretch around 2150 wave numbers. Similar to alkenes, this carbon-carbon triple bond stretch will only be visible, it will only be intense enough if the alkyne is asymmetric, or a terminal alkyne, an alkyne with a hydrogen on one side and an organic group on the other. Arenes have stretching frequencies that for the most part overlap with those of alkenes, because arenes are essentially made up of alkenes. So the carbon-hydrogen stretch and the carbon-carbon double bond stretches don't look that different from those of an alkene. The most characteristic stretch for an arene is what we call an out-of-plane bending. And this is where the hydrogens of the arene bend or wag out of the plane of the molecule. This vibrational mode absorbs between about 700 and 900 wave numbers on the right-hand side of the spectrum in what's often called the fingerprint region. And this out-of-plane bending is actually quite information-rich, even though it's in the fingerprint region. and it can tell us about the substitution pattern of the arene ring. This chart is a guide that tells us that a monosubstituted arene, one with only one group on it, will have peaks around 750 and around 700 wave numbers, while an arene ring with two groups on it that are right next to each other, an orthodisubstituted ring, will have only one stretching band around 750. So again, we can use these out-of-plane bending vibrations to help us distinguish between different kinds or different substitution patterns of arene rings. Finally, alkanes, which are organic molecules that lack functional groups, have very simple IR spectra because they have no functional groups. The IR spectrum of an alkane will have only CH and CC stretching vibrations and will look like the one shown here. What we just looked through is a lot of information about different functional groups. And when you're faced with an IR spectrum, it can be hard to know where to start. So my recommendation is to follow a sequence of steps like the ones shown here. I recommend that you start by looking for a carbonyl stretch. These are often the strongest band in the spectrum, and they appear in a region that is unique to that functional group. Then, if a CO double bond stretch is present, in step 2 you can narrow down what kind of carbonyl you have by looking first at its specific stretching frequency, and then looking for the additional stretches expected for a particular functional group, such as the CO or OH stretches for a carboxylic acid. If there is no carbonyl stretch, then in step 3, you might look next for an OH or NH stretch to see if you have an alcohol or an amine. Often organic molecules have more than one functional group, so you'll next want to look for additional functional groups like alkenes, alkynes, or aromatic rings, as shown in step 4 here. Let's end this lecture series by answering the question posed at the beginning. Given the IR spectrum shown, identify any key functional groups and then determine a possible identity of the molecule using the molecular formula given and the functional groups you identified. Here we have two pieces to use, the formula and the IR spectrum. I like to start with the IR spectrum, and I'll follow the sequence of steps we just looked at on the last slide. I'll start by looking for a CO stretch, and I have one here at 1650 wave numbers. That's on the low end of a CO stretch, so I'll tentatively assign it to an acid or an amide. And here I'll double check my formula, and I find that I have only one oxygen atom, so I can't have an acid, it must be an amide. Then I'll look for some NH stretches, because I think I have an amide. So I look on the left side of the spectrum, and I find two. Two NH stretches means I have a primary amine, a nitrogen with two hydrogens on it. And from the IR data, I know that I have a primary amide, or something that looks like this piece of the molecule. I call this a partial structure. This is about as much information as I can get from the IR spectrum. We're just going to use it to identify key functional groups. So now let's turn to the formula. And this is where those degrees of unsaturation come in handy. From the formula, I can determine the unsaturation number to be 1. So in the structure, I have one pi bond or one ring. I've already established that I have a carbonyl, so that CO double bond accounts for my 1 degree of unsaturation. So now to fill in the rest of the molecule, I need to include the C4H9 that's remaining. And I can do that as a linear butyl chain, or I can do that as a tert-butyl group. Both will be consistent with the data that I've been given. And I've chosen here to go with the branched structure.